All right, how's everyone doing? Hope that nice breaks were had by all. Let's see. Main objective for this week is going to be one more chapter. It's going to be collectively about waves and wave-like motion. We're going to focus first on the wave-like motion to help us build a context for what waves are, and then eventually we'll transition into talking about sound waves. Then towards the end of the week and start of next week, we'll do an exam prep day, open up the floor to any questions related to that, and talk about all the exam materials, review materials that I'm going to put up. And yeah, we're headed towards the end. How you guys feel? Yes?
So basically for the final, it's just whatever we've been tested on already plus this one more chapter.
Correct. Yes, one sec. And like for the final, just to make sure everyone knows, I will make a practice version and an answer key for it like I did for the tests. Question?
Do you offer any extra credit?
Technically, the tests and exam already have extra credit built in, because the tests are 105 out of 100 and the exam will be the same. I do put out a makeup lab every semester so that if you missed one, you can do that instead to make up the grade. Some students do the makeup lab even if they didn't miss something for extra credit, so that might be something once I get the makeup lab totally finalized. So I suppose technically there is extra credit in those specific ways. Does that answer the question? All right.
So like for the final, it will be twice as long, but we still get 3 hours, or?
I will be writing it with that in mind.
Okay.
Like, I don't want to make it too long that you can't finish in time. I'd say it might end up being about 18 questions, but they'd be shorter ones to make sure that everyone can finish.
Okay.
I'm going to try to cut it down from that, though. Yes?
And this is the last week for labs?
Yes, there is one more lab this week. This is the last one. Yes?
Will the format and like the way that the questions are be the same as our previous tests?
Yes.
Or, okay.
Yeah, it'll basically just be another test, but longer. All right. In that case, I'll just say again one last thing. If you didn't pick up your test last week, I still have them. You can collect them anytime. And now, for our main focus for this week, Chapter 10 will be about vibration, waves, and sound. We're going to begin today by looking at sort of the basics of wave-like motion, and then towards the end of the week transition into how that applies specifically to sound and the human perception of sound. Before we can actually talk about waves properly, though, we have to go through some vocab words and look at basically the prequel to waves, wave-type motion. So first up, a bunch of vocab words. The first of which is going to be simple harmonic motion. Simple harmonic motion is basically any motion of any object or material or part of the universe where something is going to be oscillating, technical term, oscillating back and forth between 2 points. To give a demonstration of what this looks like, I have a spring currently hung vertically here at the head of the room. I'm going to hang this mass from it. When I put the mass on it, it's naturally going to want to extend to this length. Let me actually use some smaller mass so it doesn't stretch as far. So, I've added mass to it. This is now basically the spring's default length with this amount of force applying on it. It is in turn applying force onto the mass to keep it from falling. And I am going to disturb it and trigger simple harmonic motion where the mass is going to oscillate up and down between two fixed points. The points being its lowest point and its highest point. It's constantly switching back and forth between those two positions. We call this simple harmonic motion. Simple because it's just moving back and forth, up and down. Motion because it's moving, and harmonic because it's repeatedly doing the same thing over the same, it takes the same amount of time to go back and forth. So when I say simple harmonic motion, this is the basic thing that I'm referring to. And when I say the word oscillating, if that's not a vocab word you've heard much before, the word oscillation just means moving back and forth between the same 2 points. So if it's doing the same thing over and over again, I'd call that oscillating, an oscillation. So the basics of simple harmonic motion. This thing is going to keep moving like this until it runs out of energy. And this is actually the basis of wave type motion. Basically, this can be thought of as a type of wave. We will elaborate on that. Now, using this as our first type of motion that we're going to be examining, so that spring, forgot English for a sec, that spring is currently undergoing simple harmonic motion, and there are a few different ways we can describe that simple harmonic motion that we will also move on to use to describe waves. The first is amplitude, and this is basically the term for how big is the wave, how big is the oscillation. I'm going to reset this a little bit so the movement's a little easier to see. And I'm also going to compare this to the shape that you most commonly probably think of as a wave. Does that look familiar? All right, this is sort of the most, mathematically speaking, the most common waveform that people are used to seeing. This is called a sinusoidal waveform. Sinusoidal just meaning of or referring to sine, S-I-N-E, the same sign we've been using this semester, S-I-N-E or just S-I-N on your calculator. Because if you try to graph sine of x on your graphing calculator, you get something that looks like this. So sinusoidal is just referring to that sine function that we use. And you'll often think of waves as being kind of shaped like this. It kind of looks like the ocean if you're staring at it for long enough. And the term amplitude, applied to this and also to this, measures how big the oscillation is. On a normal wave function, amplitude measures physically how big the oscillation is from its default state. In the case of this spring, if I stop it for a sec, this is where the mass natively wants to be when hanging from this particular spring. So that is its default condition. If I pull it down by, say, 5 centimeters, I have disturbed it 5 centimeters from its baseline, and when I let it go, it's going to oscillate between 5 centimeters below baseline and 5 centimeters above baseline. So the amplitude is distance from baseline that the object keeps oscillating between. It's not the total distance from top to bottom, it's from baseline to full extension. So you could measure either from baseline up to the highest point or separately from baseline down to lowest point. And that is the definition of wave amplitude. Basically, it's wave bigness or oscillation bigness, the physical size of the disruption. If I was to try to go ahead and correlate this to sound, this would correlate to volume. The physically bigger the wave, the more energy it carries, the louder it is. So the bigger the amplitude, the bigger the oscillation. The more it's shaking back and forth, and the more energy enters your ear if it's a sound wave. So when I say amplitude, it's basically wave size. Next is wave length, the physical measure of the length of one entire waveform. To try to draw that onto this diagram real quick. If you were watching ocean waves of this shape, the wavelength of the waves is the distance of one entire wave, one entire complete oscillation cycle. The symbol for that is this lambda or gamma? I forget. Sorry, say it again.
Lambda sounds more.
Lambda, thank you. This is lowercase lambda. It kind of looks like a rotated letter Y, I think. And that is the variable for wavelength in our formulas. There's going to be one or two that uses this one. It is, again, the physical distance of one entire wave. And I do mean one entire wave. If you were watching ocean waves and you wanted to measure the wavelength of those waves, you would need to start measuring from one point and measure the physical distance to the second iteration of that point. So say peak to peak, or trough to trough, or falling middle point to falling middle point. It's not from here to here. It's from one point to the next iteration of that point. Try to compare it to this, just to give kind of a similarity. You want it to lap back to where it was when you started measuring. And on this type of wave, that physical distance, the physical length the wave travels, would be the wavelength of the wave. How are you feeling so far? Wavelength is physical length. It is physically measured in normal meters. So there's no new unit yet, just a new variable symbol. Now for something that does have a new unit, frequency. The frequency of a wave or an oscillation tells you how many times the wave passes or the event occurs in 1 second. So, for example, if we're examining this simple harmonic motion right now, if I hold it down here and I let it go and I begin a stopwatch and I time how long it takes, I time 1 second and I count how many times it oscillates within that 1 second, that would be the frequency. It tells you how frequently the event occurs. If you were watching ocean waves, you'd want to count how many waves pass you in 1 second. And that would tell you the frequency of the waves, how frequently they pass you. So wave frequency is number of waves per second, or number of complete oscillations in 1 second. So frequency is number of waves or number of full oscillations that pass per second. I'm suddenly self-conscious of my handwriting. Second. Bless you. So you can measure frequency in units of 1/seconds, but there's a more common unit for frequency that you will probably be familiar with, and that is hertz. You familiar with that unit? So, 1 hertz is defined as one wave or one event occurring every second. So if something has a frequency of 1 hertz, it will cycle through one complete oscillation or one complete waveform in 1 second of time. If something has a frequency of 2 hertz, it happens twice in 1 second, and so on and so forth. To kind of scale this to sound real quick, most sounds that humans hear are somewhere around like 5,000 hertz. So if you are hearing 5,000 hertz sound, you are being bombarded with 5,000 sound waves every second. As a definition, how are we feeling this one before moving on? All right. Hertz is a new unit. It's spelled capital H, lowercase z. It does have a full English spelling if you're curious, and this is named after scientist Heinrich Hertz. The last quick vocab word we're going to do is period, referring to period of oscillation. This is basically the literal inverse of frequency. Frequency is events per second. Period is seconds per event. Instead of counting how many oscillations occur every second, if I wanted to measure period of oscillation, I would take a stopwatch and measure how the time it takes for this thing to start down here and then come back. The amount of seconds that one event needs. This is again the literal inverse of frequency. Frequency is events per second, period is seconds per event. So they have a direct inverse relationship. The symbol for period is uppercase T because it's basically just a very specific time measurement. It's time, it's just a specific, you're asking for a very specific time. And since it's time, it is measured in seconds. Period equals the inverse of frequency, and it is still measured in seconds. Because it's just time, it's just the time it takes for one event to pass. The period of this wave would be how long does it take for one whole waveform to pass you by. And it's just the inverse of frequency. Which one you use just kind of depends on what the formula in question is asking for. But if you have one, you can invert it and find the other. To kind of backtrack a second, I mentioned that if you are hearing 5,000 hertz sound waves, you're being bombarded with 5,000 waves every second. The period of those waves, if you invert 5,000, would be 1/5000th of a second. It takes 1/5000th of a second for one of those waves to travel and hit your head. So, it's a lot of vocab words up front, but we need a foundation of these terms before we start talking about the wave motion. How do you guys feel so far? And any questions on your mind here at the start? All right. One sec. Now, one of the reason that I've been showing you this, and in order to compare it to the waveform that you're used to seeing, pretty much all forms of simple harmonic motion tie directly into waves. This thing is going to constantly oscillate up and down over time, and the terms we use to describe this are the same as the terms we use to describe this, because it is basically the same motion. This waveform is basically describing the motion of this object up and down as time scales along. So one way that they used to create these waveform images is literally they would just have paper scrolling like this and have a spring like this oscillating up and down with a pen on the paper to create the waveform. So this and this are technically the same thing, and that's why we're using the terms to describe both of them. So these came from this. And really any form of simple harmonic motion can cause the same effect. We're going to come back to this later this week, but springs and also pendulums, this is not the best demonstration, but I didn't prep a pendulum today. Same basic concept. The object is the end of the cord, is oscillating between two fixed points, and we can use all the same terms to describe it. You can count the number of seconds it takes for one oscillation. You can count the number of oscillations that take place in a second, so period and frequency. Same vocab words, same basic type of motion, and the study of waves originated with this. We're going to come back to this both the spring and the pendulum later this week. Just kind of wanted to show the foundations of it first. What I want to do today is actually move on a little bit more to waves to show you some of the things you're going to be seeing in lab this week first. So, first of all, questions. All right. Next of all, let's make some waves, shall we? Amplitude is maxed. Yeah, I'll do. So, this mechanism that I have on my table right now, we've got a speaker right here, just a normal sound speaker. If you want to come up and look at it later, you can, but ripped right out of a speaker system. It's connected to this control panel, and I can use this to control what frequency that this speaker is shaking at. As it turns out, literally any speaker is just some film like this shaking up and down at the correct frequency to make the correct sound. That's all speakers are. It's just something shaking constantly at the right frequency. And right now this thing is going to be putting out whatever frequency I dial into this thing. Currently that would be 15.6 hertz. And that means that it's going to shake up and down 15.6 times every second. And I can dial in some pretty big numbers. That's about 200. Starting to get a little uncomfortable. And we'll cut it back down to a low number. Lower. There we go. Beautiful. And so I've set this up to be able to create some waves that we will be able to measure and discuss during this week. And actually, lab this week will involve you guys manipulating this very apparatus. So, take notes. Now, whenever you create a wave, you are causing some object to undergo simple harmonic oscillation, simple harmonic motion, like with that spring over there. And technically the same thing is happening here. The wave source, this speaker over here, is undergoing simple harmonic oscillation because the physical object is just oscillating back and forth between two fixed points. This speaker just moves between two extremes at any given moment, back and forth constantly, the speed of which just depends on what frequency I set it to. And I've tied a string to the speaker itself such that the string itself also starts shaking up and down, back and forth between those two extremes, those two positional extremes as well. Notice that the amplitude of this oscillation is pretty similar to the amplitude of this oscillation. So the string is basically just carrying out whatever the speaker is telling it to do. The motion is traveling down the length of the string. The motion begins here and is going to constantly travel back and forth along the string, back to this thing, and the cycle repeats itself. Again, it's simple harmonic motion. It's just doing the same thing over and over again, moving back and forth between the same 2 points until I make it stop. And the thing about waves is, all waves are just traveling energy. Energy traveling back and forth, well, not even necessarily back and forth, but energy traveling from point A to point B. Every single wave, no matter what type, is just traveling energy. If we look back at the spring here to kind of demonstrate that, if I get it moving again, just to look at the original simple harmonic motion before comparing it to the waveform in the string. We've looked at how the energy transforms in this situation before, right? We've looked at GPE and KE and EPE constantly. And if you were to use those terms to describe this motion, you would be able to tell me how the energy is transforming between different states based on what position the mass is in and how fast it's currently moving. You know, all the way down here, it's got a lot of EPE. Once I let it go, it acquires some KE as it rockets away real fast, but then it stops for a second. KE is low, EPE is lower because the spring isn't as extended, but now it's got more GPE, and then that GPE drops again as it gains KE, and then it turns back into EPE, and it's just constantly cycling between those different forms of energy. Sound familiar? All right. The energy here is constantly transforming and also constantly traveling because it is switching constantly between what object possesses it. You know, the mass will have it in the form of GPE and KE, but then at certain points the spring is going to have it in the form of EPE. So the energy is constantly switching states and also switching positions, switching what object has it. The same is true of waves, because all waves are is just traveling and transforming energy. When you create a wave, and I'm going to use sound as the main example, when you create a wave, you are putting energy into some sort of medium. And when I say medium, I'm referring to whatever material the wave is currently traveling through. That wave is traveling through the metal of the spring. This wave is traveling through the physical string. So the medium that a wave travels through is just the physical substance the wave is currently in, that the wave is traveling through. And when you create a wave, you are putting energy into that medium, and the energy is traveling from point A to point B. The medium itself actually does not travel, the energy travels. I'm going to actually turn this off real quick to try to demonstrate. So I'm going to get the string stationary. Right now, is the string undergoing a waveform? It's not a trick, I promise. No, I turned off the speaker. I am going to, rather than using the speaker, I'm just going to use my hands to pluck the string and make a wave. Now, when I do this, I'm putting energy into the string. Since it's an elastic cord, I'm basically adding EPE to it right now. And when I let go of it, that EPE is going to turn into KE, and it's going to cause the string to oscillate as the energy travels around. So I'm just going to pluck it real fast. And that sent a wave to the other end, and then that wave eventually comes back, and it keeps zipping around until it just loses energy and stops. Now, I'll just do it again. So one pluck. Actually, maybe I can make it tighter. Travels better this way. And so the energy travels from the source to the other end and then just back and forth until it peters out. Now, my question is, did the physical cord, the rope, travel with the energy? Did it travel? Some people are shaking their heads no, and that is correct. When I pluck the cord here, note that there's a certain amount of cord, carbon atoms basically, in my hand right now. And when I let go of that cord, those carbon atoms stay here. Like, they oscillate a little bit up and down, but they don't zoom off in that direction. They stay in this general location, shaking, undergoing simple harmonic motion. Those atoms don't go all the way down the cord and back. Those atoms stay in the same basic position. You can do the same thing with a spring or a slinky. I'm going to repurpose this slightly. Suboptimal. It's a little better. So I'm just going to do the same basic thing. Just going to, never mind. I usually do this on the sink, so I'll move this. I'm going to do the same basic thing I did with the rope. I'm just going to pluck the coils of the spring. That's going to send a wave down it. Note that this specific coil that I pull here, that coil didn't shoot off with the energy. That coil is in the same basic position. And that's because the medium does not travel. The energy travels back and forth until it peters out. Waves, all waves, are just traveling energy. Energy that is shooting through a medium, and the medium just happens to shake while the energy is traveling through that spot. That's all a wave is. Energy shooting through a medium, and while the energy is in a given position, that medium is going to shake, undergo simple harmonic motion for as long as the energy is in that spot. Once the energy leaves, the medium cools back down. That's all a wave is, just traveling energy optionally through a medium. That's true of every type of wave. Sound waves, ocean waves, technically earthquakes too. They're just waves through the ground. Every single type of wave. Note that for all those types of waves, the medium doesn't go shooting off with the energy. When I make sound waves, which is technically just a vibration in the air that the wave enters doesn't zoom towards you with the wave, because if it did, you'd make a typhoon every time you talked. The air molecules at my throat don't zoom with the sound to your eardrum. They just shake for a second as the wave travels through them. Same is true for the ocean, because not every ocean wave causes all the ocean to zoom off towards the shoreline. The water just kind of shakes as the wave travels through it. And again, especially true for earthquakes, because when an earthquake happens, a bunch of energy is put into the physical ground. The ground shakes for a second as the energy travels, from the fault line to Sacramento. So, all waves are just traveling energy. The matter doesn't travel along with the wave. And so when I create this wave up here, keeps resetting on. The speaker is just putting energy into the cord, and that energy is just going to constantly lap back and forth from one end of the string to the other. Sound good so far? All right. Now, since waves are traveling energy, that means they have velocity. All waves have a speed. If they are traveling energy, they have to be traveling at a speed. You've probably heard the term speed of sound before, or speed of light. Those are literally just the speed that the energy of those waves moves at. All waveforms have a speed, whatever type they are, whatever medium they're traveling through. And the way that you can find the velocity of a wave is by multiplying its frequency times its wavelength. This is true for all types of wave. And the reason this formula works is frequency and wavelength. Frequency is measured in hertz, and wavelength is measured in meters. Note that the frequency is, again, the time it takes for one whole wave. Actually, no, sorry. It's the number of waves that pass every second. And then wavelength is the physical length of that number of waves. So the length of one wave, actually, length of one wave times the number of waves that pass in 1 second. Hertz times meters. And since hertz is the inverse of period, and period is just time in seconds, hertz can be rewritten as 1 over seconds. 1 over seconds times meters is velocity in meters per second. So for every single type of wave, its frequency times its wavelength will tell you the speed of that wave. And every wave has a different speed depending on what type of wave it is and what medium it is traveling through. To quickly give an example of that, the speed of sound is most commonly listed as 343 meters per second. You are hearing sound in room temperature, standard atmosphere air. That is the speed that they are most commonly moving at. It does fluctuate a little bit, as we'll discuss, but that's the most commonly reported speed of sound in the metric system. And the speed of light, just as a different comparison, is about 1,000 times faster. No, 100,000 times, excuse me. 3 times 10 to the 8th meters per second. Light is literally the fastest known thing in the universe. So comparing the two isn't really fair. All waves have a speed, and again, that speed depends on the type of the wave and what it's currently traveling through. Light and sound are 2 different types of waves, so they have 2 very different speeds. And the speed of sound can change depending on what medium it is currently traveling through. Just to kind of skip ahead a little bit. These are some common speeds of sound in materials, including air and also different from air. This is the speed of sound in room temperature air. This is the speed of sound in 0 degrees Celsius air, the speed of sound in 100 Celsius air, other gases, other liquids, and then solids. So, speed of a wave depends on the type of wave and the medium it is currently traveling through. Waves actually tend to move slower in gases than they do in solids, because these speeds on average are the lowest compared to the liquid ones or the solid ones. And that's one reason why earthquakes are dangerous, because mechanical waves travel faster through the ground than they do through the air. They also travel through liquid faster than they do through the air. And that's why there's more echolocating creatures in the ocean than there are on land. It's easier to rely on sound when the sound is traveling faster. On land, we only really have bats that echolocate. And in the water, you've got every form of aquatic mammal. So, speed of sound depends on the wave and the medium it is traveling through. You may use this formula to calculate that speed. And one thing you're going to be doing in lab this week is using this mechanism to create some waves and figure out how fast they're moving. Questions so far? All right. We'll use this formula a little bit before we break for today. I will go ahead and add one more vocab word for you. This thing that I've created here is called a standing wave. We call it this because it's basically standing in one place. You know, it's on the desk, it's not zooming off into the void in any direction. So that's just why it's called a standing wave. It's kind of standing still in a fixed region that we can examine it. And technically what's happening here is this is a wave constantly traveling back and forth between the 2 ends of the device. And the speaker is on to just make sure it doesn't lose energy. So this is constantly refreshing the wave that is bouncing back and forth. So, just vocab word, this is a standing wave. And I'm going to try to adjust the frequency real quick. That's 1, 2. There we go. And part of the lab this week is going to involve making and manipulating this type of wave using this same mechanism. We're going to study this standing wave real quick. This wave I've created, we are going to now measure its amplitude, wavelength. I'm going to tell you its frequency actually, because that's harder to tell by sight. And then we're going to calculate the speed of the wave using just this one that I've made up here. Premise sound okay before we start doing a little math? All right. So first up, the amplitude of that wave. Amplitude is again the distance from the base state to the either peak up here or trough down here. Those are the 2 technical terms. Actually, it's crest and trough, excuse me. Crest for the peaks and troughs for the valleys. You can call it peaks and valleys though if you want. And so that distance, I don't have a tape measure. That's upsetting. Just use a meter stick. This spot right here, we call it a node, and that is the height of its default length. I'll turn it off real quick to try to show that. This spot right here, between the waves, that is the base height. And so we can use that to compare. Crank the amplitude back up. Please don't be too tall. And so the amplitude would be the distance from here, either up to the highest point or down to the lowest. That is, again, the physical size of the wave. It correlates, I'd say, most directly to volume. So from here to here, amplitude of about 1.5 centimeters. The bigger the amplitude, the more energy the wave has. So, amplitude, 1.5 centimeters. Next up is wavelength. To measure wavelength, you're going to physically measure the length of one wave, and this is conveniently one whole wave. From this end, we start, we rise, we fall, and then we're back to our beginning position. So this is one whole wave. And so to measure one wavelength, I'm just going to measure the length of this apparatus. So from here to there is 1.7 meters. I'll move this out of the way. Next is frequency, which I'm just going to tell you. This device is currently tuned to 10.5 hertz. And lastly, wave speed. We can calculate that by multiplying the frequency times the wavelength. Frequency times wavelength, 10.5 times 1.7. Therefore, the speed of this type of wave through this very specific string, I forgot to get out my calculator, but it should be like 18-ish. Yeah, just shy of 18. And so that is the speed of this type of wave through very specifically that medium, through that rope. How does it feel so far? All right. Yeah, we're just kind of reviewing the basics that you'll need for lab this week. Questions about where any of these numbers come from or what they mean in the context of this standing wave? All right. Now, I'm going to change things slightly. I'm going to adjust the frequency, and we're going to remeasure everything for the new type of wave that creates. So I'm going to physically take this and tune it to not 100. How do you do that? Let's tune it to 21. So just to show, right now we're on 21 hertz. Notice the wave looks a bit different. Instead of 2 peaks, crests, and troughs, now we've got 4. Yes?
What was it on before?
Sorry?
What was it on before?
10.5.
Oh, sorry.
So I've literally doubled the frequency. We've now got double the wavelength. Well, double the number of peaks and valleys right now. Better. And we're just going to remeasure everything to see what's changed and see what has, more importantly, stayed the same. So, go ahead and say, I doubled the frequency, so now we're at 21 hertz. We're gonna see what's different, having adjusted that. First up, we'll check amplitude. So comparing the original position of the entire rope to the highest point, that's now closer to 1 centimeter. So the amplitude actually dropped by doing this. Next up is wavelength. Now note, wavelength is the length of one full wave, and one full wave is only one cycle. So I don't want to actually measure the whole rope right now, because the whole rope right now is actually 2 full waves. Because from start to finish, we go up, down, back to start, and then once again, up, down, back to start. So this right now is 2 waveforms, one back, back and forth against one another. So instead of measuring the entire thing, I actually only want to measure half of it, which is about 85 centimeters, so 0.85 meters. So our wavelength dropped. Frequency went up, wavelength went down. And now we're going to recalculate wave speed. Wave speed is still frequency times wavelength. So 21 times 0.85. And that gives us, look at that, the same wave speed. Even though it looks different, the wave is still traveling at the same speed. Frequency and wavelength changed, but wave speed stayed the same. And that's going to be one of the things you're going to demonstrate in lab using this device. As long as it's the same type of wave in the same physical medium, the wave speed does not change. If you adjust frequency, that will change the corresponding wavelength needed to create the same speed. And this is why different frequencies of sound have different wavelengths to match, but they all still create the same speed of sound. Same is true for light. The only way to change the speed of the wave is to change the medium the wave is traveling through. And I can actually do that by adjusting the tension in this string. I pulled the string tighter, and that actually changed the wavelength that this frequency creates. If I make the string tighter, that changes the speed the wave travels through it. Okay, that rattling is annoying me now. And that will be one of the things to investigate in lab. We're going to physically manipulate the speed of the wave by adjusting the tension in the string and seeing how that changes everything and calculating a bunch of things. Questions? All right. Lecture this week, we'll continue talking about waves. Lab this week, we'll utilize the notes from today, so make sure to bring those. Let me know if you have any questions about anything. Have a wonderful day and week.
Yes.
Okay.